Hey everyone, welcome to my video on the centroids of 2D lamina using basic composite shapes. And by lamina, what we mean is just a flat piece, uniform density across the whole thing. So usually something pretty thin like um, maybe acrylic or plastic or something that's pretty uniform all the way through. You wouldn't want something with a bunch of heavy stuff on one side and light stuff on the other side. It's supposed to be just uniform density throughout. So that's kind of what we mean by that term lamina. And what we want to do is find the center of mass of these. And before we get started on these guys, I'm going to take you to this site right here. There's a link a little bit later in the worksheet I'll point out. But um, first off, if we just think of, in this one, what we can do is just color in some boxes. So if we color in some boxes, where's the center of mass? And if you think about, say, this sort of box right here, 3 by 3, you're looking at really right there in the center is going to be that center of mass, right? I have equal mass times distance no matter what direction I go in. Same thing maybe if it were a circle or anything like that. So some of these shapes are kind of nice. They have these nice, even mass times distance on each side that you can kind of look at and just visualize. And what this site does is allows you to, say, put a tack in your shape. If you hit go, it'll basically make that shape fall, except where the tack is. So it's going to tack into that pegboard, and the center of mass should fall directly below that tack. If you hit reset, you can redraw something. So I can maybe put my tack, try to do it right on the center of mass, and if I hit go, it shouldn't go anywhere for that. So as long as the center mass is directly below that tack, it won't move. You can maybe think about some other things, like if I had this sort of shape, where would it be? Notice that your center of mass can be in the gap. It doesn't have to be on the object, right? So nice case would be maybe this circle right here with a hole in the middle. Your center of mass is still in the middle, but this happens to be in that hole. In this case, if I try to tack it in the hole and hit go, it's just going to fall. It's not tacked in. So there are some limitations to what you can do with that tack. And you can play around, like what would happen if I had, maybe something like this, where things are a little bit uneven. What side would it have to go to? And just think about, well, where's the mass, where's the distance? And even though maybe there's a lot of mass on this side, if all of a sudden I wanted to maybe make not quite as much mass, but a lot more distance this way, I can, skew it to come this way a little bit. So that's sort of the idea with this. You can just play around, it'll show you where that center of mass is. Now, what we're going to do is look at how are they calculating where that point is. So that's going to be the next thing we want to look at. So what we can do with these, we're just going to do rectangular right now, but it works for a lot of different shapes where you know what the center of mass is going to be for those guys. And what we want to try is splitting this into rectangles, and you can split it however you want. I'm going to maybe draw rectangle length down this way. Maybe we'll cut this piece off right here, and maybe we'll cut this piece off right here. So I got 4 rectangles there. There's a lot of other ways you could break it up. You could even just break it up into individual pieces, but you're trying to do kind of as few as possible along these guys. So that's kind of the idea. Is I got these 4 rectangles, and I'm going to find the center of all 4 of those. We do need to put kind of a coordinate system on this thing. So I could call maybe this corner 0, 0, or this corner 0, 0. It doesn't really matter. for this one. So let's just call, for the sake of argument, we'll call this our origin. So this is going to be 0, 0 right there. There's our coordinate system. And if we look, we're going to be, what, 2 over for this rectangle, and then looks like 1, 2, 3.5 for that center right there. So this would be at a coordinate, let's say 2 and 3.5, that guy. Oh, let me fix that. Alright, so got that fixed. Fixed my line a little bit too. This top square, we're going to go 1, 2, 3, 4 over. And it looks like 1, 2, 3, 4, 5, 6 up. So that would be at 0.46. And I'm just write these a little bit bigger there. Alright, so I went ahead and calculated out these other two, wrote them down. So this middle one we got right here at looks like 1, 2, 3, 4. That should be 4.5 and 4. So I'll go ahead and fix that one. So we got 4.5, 4 right there, and then should have 7, 4 right here on the last one. So those are all my coordinates right in the middle of those rectangles, and we're going to calculate the moments just like we did with point masses. So we're going to take how far am I from the x-axis here, how far am I from the x-axis going up, from the y-axis going over, calculate those mx, my values, and then divide by the total mass. So let's go and get the masses of all these. Now the mass, what we're going to do is you can kind of think of it as like having a density 1, where we're just going to count the area of all these guys. So this one has 1, 2, 3, 4, 5, 6 squares in here. So my mass in this one is going to be 6. This one, it's 2 by 2, so mass in this guy is going to be 4. So for a lot of these, we're just thinking of the mass as kind of the area matching with, say, a density 1 on these guys. The reason that works is we're multiplying mass in this one, we're multiplying or adding up masses in the other one. If they were heavier, the densities would divide out. So it really just depends on how much area is there for these guys. So we got 1, 2, 3, 4, 5, 6 for this one. There's a 3 by 2, and then we got 4 by 2 here, so mass is 8. Alright, so which is 8. We'll go ahead and write down the calculations for this real quick, and I'll just write them down, and then we'll go through it. Alright, so what we have here is the my, so the 6 times 2, 4 times 4, 6 times 4.5. So again, I'm looking at these x distances across times the mass for those. So you end up with just the x times the mass for all these. So 6 times is 2, 4 times is 4, 6 times is 4.5, and then the 8 times that, 7. That totals up to 111. The mx's, you're looking at how far are you from the x-axis, so the y distance. So this is going to be 6 times the 3.5 going up that way. And then same thing for the other ones, you're just mass times height, so 4 times 6. Again, another 6 times 4 here, and then the 8 times 4 for that last one. So that's where you're looking at for those guys. And I just realized that I think this is actually a y value of 3 and not 4. 1, 2, 3. So I'll go ahead and fix these real quick. Alright, so the last part, got those numbers fixed now. Last part is we're going to divide these out. So my x bar and y bar will be these my and mx over my mass 24. So if you want the fractional form, you can actually just put in that 111 over 24. Again, this is my my, and a lot of times I compute that first just so I can go in order. But remember, these are x distances, so they go with the x bar. And then the 93 over 24 for the y bar. 93 over 24. And if you want to put that into your calculator, get a decimal, we can see approximately where that's at. So the 111 over 24 is about 4.625. So we'll say 4. After that one, 93 divided by 24 is about 3.875. We got 5 for that one. So that'll help you maybe plot it a little bit. So 4.625, that's a little more than 4.5, so around here-ish. And then 3.875, 3 is right there. So maybe like right in here at the top of where that 4 is located would be my center of mass. So that's what I'm looking at right there. That kind of gives you an idea of how these go. I'm gonna let you guys try that one on the right on your own. If you want to pause the video, go ahead and pause it. We'll go ahead and take a look at this one next, and just find the center of mass of this composite shape right there. So pause the video, go ahead and try to calculate it out. I'll write it out here, and then you can check your answer real quick. Alright, so hopefully in that time you got these values right here for my, the 143. So you're getting this 4 times 4. Again, this is from the y-axis, so going across. So 4 times the x of 4, 18 times 5.5, 4 times 7, all adds up to 143. The mx, the 4 times the 6, so you're going from the x-axis up, so times these y values. 4 times 6, 4 times 18, 2 times 4, you get 104. Masses are 26, and you divide out the 143 by 26, 104 by 26, and you get 5.5 comma 4. So that is the final answer for that center of mass. Now if you plot it, notice where that's at. That is right here, exactly at the same point where that center of mass was. And if you look at this a little closer at the beginning, you'll notice this is very symmetrical. You have this sort of 2x2 block that's above here, this 2x2 block that's the same distance below that center of mass line right there. So you can kind of put in this dividing line all the way across here, and you have the same masses times the same distances across that whole line. So that 2x2 block is the same distance there as it is here. Again, it doesn't matter left or right where it's at in terms of this line. So we know the center of mass has to be on that line just because of some symmetry. By the same argument, I could draw a line right here going vertically at 5.5, and it's the same deal. You got for this big rectangle the same amount of mass and distance on both sides. These two smaller rectangles or squares are also the same distance from that line, even though they happen to be above and below. It doesn't matter, just horizontal distance in this case. So you could use some symmetry to argue that that should be where the center of mass is right there, and the calculations justify that as well. So that'll do it for this video. There are, so here's the website where we saw that sim bucket. You can use that to check your answers later. There's some homework here at the end if you want to try these. Some answers there at the bottom. But go ahead and try those for your homework, and that'll do it for 2D center of mass with point masses and composites.